This is our introduction to the experiment proving why lemons are more acidic than oranges. I'm going to start off with talking about acids. Acids and bases react with one another in a neutralization reaction to form a salt. This is also the basis of buffers. An acid is a solution that has more free hydrogen ions than hydroxyl ions and a pH less than 7. An acid is a substance which reacts with a base. Commonly, acids can be identified as tasting sour, reacting with metals such as calcium, and bases like sodium carbonate. Aqueous acids have a pH under 7, with acidity increasing the lower the pH. Chemicals or substances having the property of an acid are said to be acidic. Common examples of acids include acetic acid in vinegar, sulfuric acid used in car batteries, hydrochloric acid used in stomach for enzymes, and tartaric acid used in baking. As these three examples show, acids can be solutions, liquids, or solids. Gases such as hydrogen chloride can be acids as well when dissolved in water. Strong acids and some concentrate weak acids are corrosive, but there are exceptions such as carboranes and boric acids.
A base is a solution that has less free hydrogen ions than hydroxyl ions and a pH of more than 7. A base in chemistry is a substance that can accept hydrogen cations or more generally donate a pair of overvalence electrons. A soluble base is referred to as an alkali if it contains and releases hydroxide ions quantitatively. The quantitative theory defines bases as proton acceptors, while the more general Lewis theory defines bases as electron pair donors, allowing the other Lewis acids than protons to be included. The oldest Arrhenius theory defines bases as hydroxide anions, which is strictly applicable only to alkali. In water, by altering the ionization equilibrium, bases give solutions with a hydrogen ion activity lower than that of pure water, that is, a pH higher than 7 at standard conditions. Examples of common bases are sodium hydroxide and ammonia. Metal oxides, hydroxides, and especially alkoxides are basic and counter anions. Of weak acids are weak bases.
Titration, also known as titrimetry, is a common laboratory method of quantitative chemical analysis that is used to determine the unknown concentration of an identified analyte. Because volume measurements play a key role in titration, it is also known as a volumetric analysis. A typical titration begins with a beaker or Erlenmeyer flask containing a very precise volume of the titrant and a small amount of indicator placed underneath a calibrated burette or chemistry pipetting syringe containing the titrant. Small volumes of the titrants are then added to the titrant and indicator until the indicator changes, reflecting arrival at the end point of the titration. Depending on the endpoint desired, single drops or less than a single drop of the titrant can make the difference between a permanent and temporary change in the indicator.
The materials we used for our experiment was a burette holder or a burette stand and a burette and a flask and a magnetic stirrer. And we had a lemon and a orange, and we had the indicator called phenolphthalein, and the chemical we used was NaOH, I think.
It wasn't. It was A.
It was A?
No, it was?
It was NaOH.
Yes, it was.
Yeah, NaOH. Okay. So we had 10 milliliters of the orange and the lemon in 2 different flasks. And then we put 5 drops of the indicator, which is the phenolphthalein, and 50 milliliters of water. So we put a magnet in the flask, and we put it on top of the magnetic stirrer, and we poured the NaOH on the water and lemon. For the lemon, we refilled the burette about 4 times to get a correct a number of.
We can just talk to the person about maybe going to somewhere else during chemistry. We should probably.
Yeah. So our calculations for the citric acid and lemon, we have 3 questions. First of all, calculate the NOH, and then we look at the relationship between OH and H3 and the ratio is 1/3. And then we have to calculate the C-sit in the 10 centimeter cube juice we used. So first of all, we'll do the lemons, and so we have 0.1 moles of a liter multiplied by 0.095 liters of HCl we used, and the answer is 0.0095. And then when we look at the reaction between the relationships, we have N-sit equals 1/3 multiplied by NOH. And then the answer is 0.0095/3, and then it's 0.003166 mole. Calculations with the C-sit in the 10 centimeters cube juice, it's 0.00316 over 0.01 equals 0.3166 mole. And that's our answer. That's for the lemons, and for the orange is 0.1 mole over liters multiplied by 0.02 liters equals 0.002 mole. And the relationship between OH and H3-sit is N-sit equals 0.002/3, and the answer is 0.00066 mole. And then the calculation in the 10 centimeter cube juice, it's 0.0006 over 0.01 equals 0.066 mole. So, in conclusion to like these calculations and the reaction we had with the juices, we would find that lemons are more acidic than oranges because lemon had used more time and used more solution to change the color instead of orange, since orange only used like 22 milliliters, while the lemon used 95 milliliters of the solution.